Okay, so I will tell you about something else, which is highly related to the last thing that Tatiana was telling us in her talk about the relation between the canonical, the covariant formalisms. She was focusing on, of course, in the case of gravity, in the first order formulation, but I will talk more in general and then well, have some comments and then some questions. Okay, so the motivation is that we know that there are at least two main different paths for the classical Hamiltonian analysis of these theories, and they are known directly as the covariant approach and the canonical methods. Right? So the canonical always involves 3 plus 1 degree and 4 dimensions decomposition of an action, and the covariant, as we've heard several times, is based on the space of solutions to the covariant equations. So they're based on different structures, but the normal expectation is that they should be equivalent in some form, right? So, and many people, some communities have worked on this assumption and not challenging it too much, but we've been forced through the example we have been looking at, especially when we have boundaries, that this is not exactly the case always. So there are differences, and that's something I will tell you about. Okay, so if we include boundaries in the region of the consideration, for instance, if we want to consider black holes as an interior boundary of the region, that's something we have to deal with. So that imposes challenges for both methods, both canonical and covariant, but the assumption of equivalence is also persistent in the community. Okay, so we were interested in exploring precisely the possible equivalence or non-equivalence of the symplectic structures. That's the thing I will focus mainly, and the corresponding phase spaces. Okay, so probably the intuition that these two methods give you the same is based on the simplest gauge theory, which is Maxwell's theory, which is too simple. And in that case, it's very easy to see that they're actually the same. So that's probably what have fueled this assumption that they're always equal. Okay? So I'll just tell you about the quick comparison of canonical and covariant methods, just to set the notation, to say. Then that will include boundaries in both cases. And then tell you about this equivalence of the output. Okay, so here I have summarized what are the main features of these two approaches. So the canonical approach is here the phase space, the canonical phase space, naturally arises as a symplectic map. So this is, if we have a configuration space, then naturally this is the cotangent bundle of the configuration space, so there's no ambiguities in what the canonical phase space is in principle. This normally in field theories, of course, we're talking about, it implies a 3 plus 1 decomposition of 4-dimensional fields, n plus 1 is the decomposition, we are in dimensions, n plus 1 dimension. For gauge theories, which is what we're interested in, there are constraints. So we have the phase space, which is a cotangent bundle, we have to restrict ourselves to a class of manifold, which is defined by the constraint surfaces. In that restriction, normally what happens is that if there are first-class constraints, the pullback of the symplectic structure is degenerate, which is precisely what gives us the gauge direction. And then we know that the development of this is that there's not, in the case again of first-class constraints, there's not a unique Hamiltonian, because we can always add terms which are proportional to the constraint, so we really have a non-unique evolution, so to say, right? here we do have relation between the Hamiltonian and Hamiltonian vector fields because we can always use a non-degenerate symplectic structure on the kinematical phase space, but the ambiguities, so to say, come in the many possible Hamiltonians. Now, in diffeomorphism invariant theories, which is what we are interested in gravity, for instance, coupled to other fields, the Hamiltonian normally has some bulk term, which is normally a sum over the constraints, plus a boundary term, which gives us energy, for instance, if we are looking at time translations at infinity or time translations at the horizon, as Tanya was telling us. And the important thing about canonical approach is that this is a starting point for canonical quantization. This is, for loop quantum gravity, this is very important. Of course, you can always try to do path integral, but in terms of canonical quantization, this is what we need. Right? The covariant phase space, on the other hand, is based, or covariant is defined as phase space as a space of solutions to the field equation, which is very different from the kinematical Hilbert space we started with, which is the cotangent volume. Now we don't need, in order to define the phase space, composition of the space-time, which is constructed from the entire history, solutions of their histories. In that case, there is a specific procedure given an action how to find the symplectic structure, which we call mu omega here, opposed to the capital omega for the canonical approach. Now, in this case, the Hamiltonian is well defined, and what happens is now that the Hamiltonian vector fields are non-unique. So we have the same indeterminacy, but it comes in different places. Now, for the diffeomorphism invariant theories, the Hamiltonian, which is well defined, has only a boundary term, right? So there's no both terms. It's only, when they show, it's very easy to see that it's always boundary term. And now the problem with this is that while this is very beautiful as a classical formalism, we really don't understand how to use it as a starting point for quantization other than linear quantum theory, which is rather tricky. Okay, so let me just go. A common starting point in both cases is a set of fields and an action given by some Lagrangian density. Possibly, we may possibly have a boundary term to make the action well defined, so differential. Here we are considering a region which is of the form sigma cross R, region under consideration, with a boundary, which could be either exterior boundary or boundary, exterior and interior boundary, and in a globally hyperbolic space-time. So the boundary has an initial Cauchy surface, final Cauchy surface, probably some term at infinity, and probably some inner boundary, which could be, for instance, an isolated horizon. Okay, so in order to have a well-defined variational principle for given boundary condition, for a finite action, one might need to add some boundary terms. We know that in asymptotically flat gravity, we need to add extra terms to satisfy all these requirements. So, always a possibility. Okay, so now what happens in the canonical approach? So what we do is a 3+1 decomposition of the whatever action we have, and we write down the covariant action. And then, which is written in this way, so these are some b derivatives of the fields with respect to the time translation vector field that we have chosen. And so this gives us exactly what is the kinetic term, and that is going to give us information about the symplectic potential and the symplectic structure. And whatever is here is what we call the Hamiltonian. And this kinetic term may have normally has a contribution from the above, but may also have a contribution from the the details of the action we're looking at, boundary conditions, boundary terms, and reaction, and so on and so forth. So we may have a contribution from the boundary. Now, I'm calling this bulk canonical variables, which is appearing here in this part of the bulk. And these fields, which I'm using different notations, are interpreted as boundary. And in some cases, but not always, they are pulled back of the bulk variables to the boundary, but not. Sometimes we have found cases in which the momenta, for instance, is not a pullback of anything, it's just something which is intrinsically living on the boundary. Okay, so this was developed in a paper with Tatiana just a few years back. So from there we can read off the symplectic potential from this term, and then arrive at the symplectic structure just by taking the exterior derivative on phase space. So we do get this standard thing we expect on the bulk, and we do have a contribution from the boundary. We have now a boundary term. Now the important thing in this case is always in Hamiltonian dynamics is Hamilton's equations, which relates those Hamiltonian vector fields via the symplectic structure with the Hamiltonian generator of symplectomorphisms along this Hamiltonian vector field, and that's how these are related. Right? This is Hamilton's equations are inside if we choose a stage the Hamiltonian generation and evolution. Now, in general, for a gauge theory, the form of Hamiltonian will have some combination of constraints plus some boundary terms. So these are the bulk first class constraints. Now, there may be also canonical Hamiltonian, which is non-vanishing. If we have a diffeomorphic nematic theory, of course, there's no such contribution, and we only have a linear combination of constraints. Okay, so we do have a boundary. There are two possibilities depending on the form of the canonical action. One possibility is that omega has a vanishing contribution from the boundary, so meaning that we do not have this term, so we only have a bulk integral here and no boundary integral. So if that happens, this is precisely what is called the standard Ray-Tytelon scenario. Okay. Ray-Tytelon scenario, which was developed for asymptotically flat gravity, basically they tell us that their prescription is that whenever we take variations of any function, we should, and we do get boundary terms, we have to kill those boundary terms. And because if we don't kill them, the function is non-differential. That's why they do it, right? So here, one of the messages is that is not the full picture. There are instances in which we have to do that, precisely this one. But there are other instances in which you should not do that. If you do that, then you get wrong all the equations. So here are examples of this Ray-Tytelon type of theories is, for instance, Maxwell theory. In that case, we will not get contribution from the boundary to the symplectic structure. If we add to Maxwell the topological term or triangle term, so the same case. And of course, the case that they were looking at, which was general relativity, was with asymptotically flat boundary. Right? So if you only have that as a boundary, then what they were telling us was okay. Okay? But the other possibility is that we do have a contribution to the symplectic structure, namely that this term is different from zero. And in that case, well, then we have to do something else, right? Because in that case, in that case, there's a boundary contribution, not only, to everything, right? So this equation has to be satisfied. Right? So if the right-hand side has a contribution from the boundary, means that the Hamiltonian vector field may have also contribution from the boundary. And the left-hand side may have contribution from the boundary. So that means that we cannot, when we compute this gradient or variation of age, we cannot just kill the contributions from the boundary. They have to be there because they have to be equal to whatever contribution from the boundary we have on the right-hand side. So it's a very simple observation. Okay, so in that case, the examples are, okay, well, Maxwell here is from the Maxwell cluster assignments. This is, of course, just a theory which is living on the boundary, so it's not a surprise that we do have contribution from the horizon there, from the boundary. And for instance, the example that Daniel was talking about, which is first order gravity with isolated horizon as an internal boundary. In that case, we also, in some instances, we do get contribution from the horizon to the symplectic structure. Okay, so now what happens with the covariant approach? Well, in that case, we do have same starting point and an action. When we take the variation of the action, we get a bulk term, which is just proportional to the equations of motion. And then sometimes we get always some boundary contribution, which is basically obtained by integration by parts. This is the kind of term that Professor Kijowski was talking about in his lecture. So it's the starting point for defining in this case, the covariant symplectic potential. Okay, so the symplectic current, which is again the zero derivative of symplectic potential, is conserved basically because we are taking second zero derivative. That means that this quantity, which is over the boundary of the region of the consideration of what is called the symplectic current, has to vanish. And that means that depending, of course, on the boundary conditions, on fields and the variations, for instance, if the symplectic current vanishes at infinity, and also this integral vanishes at the internal boundary, for instance, then this means that these two terms are equal, and then we can just postulate that there is a conserved pre-symplectic structure given by this integral over any Cauchy surface, because of this property will be conserved. That's how we get the symplectic structure in this case. It was very elegant, very nice. Now, of course, there are some subtleties. Now, the thing is that this is the symplectic potential, which has, we have maybe of this form in general. We could always have exterior derivative of something else. In this case, we need to add a boundary covariant action, which is what this is. But this thing is arbitrary and does not contribute to the symplectic structure, because when we take the exterior derivative of this to get the symplectic corrected, this gets killed, right? So this means that whenever we have a boundary term added in the original covariant action, or if we have a topological term as the one in Pontiac, then this term is not going to contribute to the symplectic structure. In the case of first order gravity, when we have an isolated horizon, which was the case that we just heard, one obtains that the contribution from the horizon to the symplectic structure, to the symplectic current, is a total derivative, so that allows us to integrate it over the boundaries of the delta. So in that case, the conserved symplectic structure has the standard bulk contribution for first order gravity, and now we do get a contribution from the boundary. And that's exactly what this is what Ashkai and so on did more than 20 years ago. Okay, and again, we don't have a contribution from the asymptotic region for asymptotic flags. Okay, so now in that case, the Hamiltonian for vector fields which are given by lead derivatives of the field, so that's the notion of some motion along some vector field of the manifold. This is always at the general direction of the presymplectic structure of diffeomorphism invariant theory. Because this only has a contribution from the, I mean, in order to see that this is at the general direction, we have to show that this is the case for any arbitrary vector field. If the theory is diffeomorphism invariant, then we know that this has only contributions from the boundary. If this vector field happens to vanish at the boundary, then the corresponding Hamiltonian vector field generates H transformation. So this is a generalization of what is called in ADM the bubble time evolution, for instance, that we know that this is gauge. So this is the equivalent. If we have a vector field which vanishes at the boundary, then we have a different direction. So this is the present structure. Okay, and also in some cases non-vanishing vector field at the boundary also defines a gauge direction that will depend, of course, on the details of the theory under consideration. Now, if this is different from zero on the boundary and it's not at the general direction, then we can find a Hamiltonian again by solving this Hamiltonian solution. And this is a Hamiltonian conserved charge associated with symmetry generated by the vector field. In this case, I mean, one can see that the canonical and the covariant Hamiltonians coincide in a sense. No? So that's why this is all there. Okay. So then now let me go to this idea of what happens with the equivalence of the symplectic structure. Right? So you know that in many aspects of the two approaches are equivalent. But the equivalence of the symplectic structure has been proven only in very simple concrete examples without boundaries. As I was saying, Maxwell theory is a pretty interesting case in which they are both equivalent. So both the presymplectic omega and big omega and small omegas look the same, and even when they're defined in different spaces. Right? So this is a tricky question to ask the equivalence between two things which are living on different spaces. Because one is living on the space of solutions to the Maxwell equations, and the other is living on initial data satisfying Gauss's law, right? Which is the pullback to the constraint surface. Okay? So even when we are strictly on different spaces, they look the same, namely the canonical conjugate object to the connection is the electric field, basically. So that's why we say that the electric field is the canonical conjugate moment to the vector potential, to the magnetic potential, which is a configuration space in that case. Okay, so but now, I mean, we're not the first people trying to think about this equivalence. There's a recent paper which came out last year, the Madrid group, and they claim that the equivalence of both symplectic structures in general, rather general first order theories in reduced to boundary. It's a very strong claim. And I can say that I don't quite understand their proof, but I'm very confident that there are examples in which this is not true. And they have explored the fact that in some situations the covariance symplectic structure can have a boundary term of this type. Okay, so this is just my last slide. So it's not clear if the result is general enough what they are claiming. Exactly true always. In particular, there are examples of first order theories where the non-equivalence is clear. And this is an example I was already telling you about, which is Maxwell's laws from Piagni. In the covariant theory, there's only a Volt term, which is in this symplectic covariant symplectic structure, which corresponds to the Maxwell case. The Pontriani doesn't contribute precisely because it's a topological term, so it is zero its contribution to the symplectic structure. Or in the canonical description, if we look at the just canonical case, we have an extra boundary term. So we have the bulk Maxwell symplectic structure plus something which can go to the boundary, which is would be precisely the symplectic structure of a Chern-Simons here. We don't have a Chern-Simons theory, but that would be its symplectic. So this is a very simple example, and we do have very different symplectic structures at the level of kinematical levels of the system. And also very striking example is just the topological theory, the Pontiac case. In both cases, these two omegas look very different. In the covariant one, we show that this is exactly zero on all possible configurations, that there are no equations of motion, so any configuration is a solution, but the covariant omega is exactly zero. Now the canonical is not zero in the kinematical phase space, of course, because this is the canonical cotangent bundle. But if we look at the pullback to the constraint sources, that then it becomes fully degenerate, which is therefore equivalent to zero. So in a sense, at the end of the day, there's equivalence at the level, of course, the reduced phase space, but not in the first steps of the procedure. And also something that Tatiana mentioned, that we've shown that in the case of gravity, in the first order formalism, the symplectic structures are not equivalent. So the covariant one that Jurek and Ashley have obtained a few years ago is not the same as the ones that one can obtain in the canonical procedure. So this is something we published last year. Okay. And then, so open question is exactly when and how, why this is equivalent or not. So, thank you.
So it's time for questions.
So I have mixed feelings about the relevance of all those ambiguities and all those boundary parts of symplectic form or of the consequences. So for me, this if we come up with some tricky boundary term which improves properties of the charges and currents that we define, okay, then we gain something. Otherwise, we just each equivalent, different but emitted by non-ambiguity symplectic form will just give us different charges and different currents, which also will satisfy the balance law according to the equations of motion. So I don't see in this any deep problem, any objective problem. This is the question of diversity. In how many different ways we can define some quantities that are conserved or that evolve in such a way that we control the evolution in terms of some fluxes. So if we find such that have nice physical properties or mathematical, that for instance flux is positive definite, flux of current is positive definite, then we are happy because that quantity will always be monotonic.
Okay, so if I may answer?
Yeah.
So I think you're asking the question in the wrong dot. Maybe Laurent Faraday had talked about something, then you could ask this question. I'm not talking about the freedom of the changing the charges or anything like that. I'm just talking generic about looking at these two formalisms and then seeing exactly whether they're equivalent or not at the structural level, right? Of course, when you look at the test, you have specific boundary conditions, specific terms and so on, and then you can talk about charges and all that. So that's that is specific to. So that's one. The other is that we are not introducing any fields as Laurent and friends do, for instance. So we are not promoting any boundary degrees of freedom to satisfy something or the other one. That's not kind of thing. We are just looking at starting point as the bound, as the action, and then see what happens with these two different ways of arriving at the Hamiltonian description. That's it. So, I mean, I basically agree with your comments. So I'm just saying that this is not what we are doing here.
Okay, so I brought up I made several steps in my mind, and I asked myself, okay, so if there are those differences which here Professor is talking about, what are the consequences? Well, Einstein equations are the same, or are they different? The same. Okay. So what is different? What can be different is, as far as boundary conditions are concerned, they are up to us. We decide. We, using some physical intuition or some mathematical intuition, we decide what kind of solutions we want to consider. So again, those differences will not affect such. So the only thing that may be affected by those ambiguities are concept quantities that we define. So that's why I immediately jumped to something we were not talking about.
Yeah, exactly. So yeah, I agree with that. But here, part of the cautionary tale is that canonical some colleagues, they want to define, for instance, the covariant, the canonical complete structure, for instance, for black holes, if you want to do quantum black holes. But they start with the covariant, and then they do something weird, and then they claim that whatever they get, and they claim that they get a contribution from the Holster to the symplectic structure and that is just not what happened. So it has consequences because there have been many papers written in the low quantum gravity community claiming some results regarding the symplectic structure and the contribution of the Hall's action to the horizon, which first came from covariant methods and second fishy covariant methods. So it has some immediate consequence that, of course, at some point will manifest itself in charges and so on, but it's more basic than that discussion, I think. That is not, people are not discussing this issue.
Okay, so do we have more questions? If not, then let's